All right. 6, 7, number 4. This one involves a weed whacker, which consists of
Carol Baskin. She killed her husband. She whacked him. You can't convince me it didn't happen. She fed him to tigers. They snacked him. Carol Baskin.
that's my wife Carol. And like I said, this problem, or was trying to say, this problem involves a weed whacker. Much like, yeah. All right. So there's a weed whacker, which consists of a spool of wire, which then can feed out to the wire or the stick, as I'm going to call it, for the rest of the problem, that actually hits the grass. So this thing spins around, and the little stick here of wire spins and hits the grass, and that's how you weed whack your husband and feed him to tigers. The question asks for, it proposes that the weed whacker starts at rest and speeds up to some speed that's given. It gives it in, I got some glare going on, it gives it in revolutions per minute. You're going to want to make sure you convert that to radians per second. So that's important. So your power average is any change in energy of your system over the amount of time it took. So for this case, the change in energy is kinetic, and that's going to come from whatever's powering the weed whacker. So it's doing some work, boom, that's increasing the kinetic energy. So we can figure out the change in energy by looking at the change in kinetic, the initial kinetic energy is 0 because it starts from rest, which means we have 1/2 I of the system times omega squared divided by the time. The hard part about this problem is figuring out the moment of inertia of the spool plus the stick that's doing the weed whacking. All right, so that's the tough part of the problem, is figuring out the moment of inertia, because we need that. The omega is given, the time is given, so all we really need to do is figure out that moment of inertia. Okay, so the weed whacker consists of this spool, which the mass of the spool is given. I think it's like 100 grams or something. Make sure you convert that to kilograms. So again, much like the other problem we did, this spool has some thickness. So the moment of inertia of a thick spool or a thick-walled cylinder, you can look up on your cheat sheet, 1/2 mass of the spool, R2 squared plus R1 squared, or vice versa. Doesn't matter. And then you have the stick. The stick is kind of interesting because it's not rotating around its center of mass. It's rotating around this point over here, making this long sweeping motion instead of rotating around its center or even rotating around its endpoint. It's rotating way over here, so the whole stick sweeps out some area. So the moment of inertia of our stick, we're going to have to use the parallel axis theorem because we're not rotating around the center. We're not even rotating around the endpoint. We're rotating around a parallel axis way over here, and that's so we're going to have to parallel axis theorem to that point. So parallel axis theorem says the moment of inertia about the center of mass for a stick, that's 1/12 mass of the whole stick times the length of the whole stick. So the whole length of the stick here, which is given in the problem. So that's the moment of inertia around the center of mass, plus the increased inertia from the fact we're not rotating around the center. Is the further we rotate around the center, the more moment of inertia we're going to have to add, and that's what this term hints here in the parallel axis theorem. Using the entire mass of the stick plus the distance we've moved from the center of mass to the new axis. So for us, the new axis is still at the center of the hoop, so we're moving from that axis of the center hoop all the way out to the end of the hoop, R2 given in the problem, plus then up to the center of mass, which is L over 2. So that's what we have here. So this is the distance we've moved the axis of rotation from the center to this new parallel axis, increasing the moment of inertia by this amount. So that's your moment of inertia of the spool plus the stick. That's the hard part about this one. The rest is then kind of pretty straightforward. So moment of inertia, hoop, look it up, cheat sheet, thick cylinder. You got to do the parallel axis theorem for the stick, moving that distance from the center of mass over to this new axis of rotation. Like I said, average power is the total change in energy over the total time it takes. We can find that by doing 1/2 I omega final squared over the time. So we have all those things now, basically just plug and chug. For part B, so hopefully part A works. For part B, though, they actually ask a question about instantaneous power when the weed whacker is actually whacking at some weeds or at some grass or whatnot. So for instantaneous power, we've got to look at what's happening at that instance, because, like, I don't know if you've ever weed whacked, the thicker the grass you're trying to weed whack through, the more power you need. So a more powerful weed whacker can cut through thicker, stronger grass, where one of those weak plug-in weed whackers, they don't supply enough power to actually do enough to cut thick grass. So instantaneous power, it's kind of the same thing. Delta E, total change of energy over change of time, but we can look at the work done in that amount of time, and we can look at what amount of work is getting done at that instant in time. So work being force times displacement, or dot displacement, divided by time. Noticing we got that lovely relationship, delta x over delta t. That's velocity. So instantaneous power can be found by looking at the force that your thing is putting out times the velocity that it's moving at. And that can be your instantaneous power. Or, right, force, velocity. Or, in terms of rotational dynamics, torque times angular velocity. So we have our equivalents there, much like all our rotational equations have their linear counterparts, right? So if we have force, velocity, torque is counterpart of force, and angular speed is counterpart of linear velocity. So we can do that. So all we really need to know is the torque or the angular velocity, or vice versa. So here we go. Part B, here's your spool. Woo, woo, woo. This guy's spinning up. Here's the stick. It's hitting these weeds, right? It's trying to cut the weeds or the grass, whatever. So there's the force in the weeds. Third law says then the grass is going to push back on that stick as it cuts through the grass. So then you have your force by the weeds on the stick. And that's really the force we need to use. So if we're doing force times velocity, then the force is the force given. And that force in the problem is being applied to the very end of the stick. So that means we need to find the linear velocity at the end of the stick. So using our translational equation, omega r is our linear velocity, we can figure out the instantaneous power, making sure we're using the right radius. And in this case, I believe the radius we need to be using is all the way from the center of rotation, r2 to the spool, plus all the way to the end of the stick, L. So in this case, our r is the r2 plus the length of the stick to get our instantaneous power. And that's how you weed whack. Don't whack your husband. Don't feed him to tigers. Like and subscribe.